I will pass it on to Pietro at Pliant Energy.
There we go.
Hi, everyone. Can I be heard?
Yes.
Okay. Thanks for coming. So I'm going to do a quick overview of Pliant Energy Systems' robotic platform. It's very different. It's very unique. It has some unique capabilities. And the purpose of the presentation is to make people in the ecosystem, DoD offshore ecosystem, aware that this technology is coming, to show the progress that we've made so far, to highlight what's coming, and to show some examples of its potential application. We're a small private R&D company. We're based in the Brooklyn Navy Yard in New York City, and I'm going to start. I'm going to start with a video because rather than try to explain how different this vehicle is, I'm just going to show a video. Hope it's streaming okay. So it's a service vehicle. It's a subsurface vehicle. It is a land vehicle, and it uses undulating fins instead of propellers, which is why it's able to make the transition from land to water. So in this video is just showing that one thing you might notice is that it has there's a very tight coupling between what the fins are doing and what the robot body is doing. So when the fins undulate, it moves in a very, so here it's towing a person. This is an example of a deployment at the beach. And we chose very shallow water to show it can actually come out of the water. It's using the same fins for swimming, as you can see, as it is for crawling. Its swimming properties, okay, the crawling properties here is that it has a very tight, it can move reasonably fast on land. It can move on slippery surfaces, and there are different type of fin edge treatments, as you've probably seen. This is an earlier prototype we call Velox, just to show some of its maneuvers. It goes straight up and straight down by flapping its fins. It again, it's launching from the shore, and it has very quiet operation. Now, critically, it's also an excellent ice skater. So it's actually its happiest mode of transport is ice. Its second happiest mode of transport is swimming, and the third one is land. When I say happy, it means how many watts of battery power are being consumed for the amount of forward progress that it's making. And I show the ice skating at the end. And I'm going to do a quick slide on the relevance of ice skating. If you bear in mind, this is one vehicle that is a multi-domain vehicle. So we've had, there is a program called the MADOS program being headed up by the United States Marine Corps. It's a program that has not begun. We responded to an RFI last year. We're waiting to hear future announcements. And this is a public slide from the Industry Day from USMC. And the yellow arrows are pointing at, if you can see it at this resolution, the yellow arrows are pointing at these little black spheres, which for the purpose of this public presentation represent what the MADOS organizers are calling the MADOS Light vehicle. So the MADOS Light vehicle, we think we're a perfect candidate for that. It's an autonomous or semi-autonomous platform that can be transported on land on a larger vehicle that can move over land, that can transition through the surf zone, and that can also move on the surface and under the water. One thing that's different about our platform from the little black spheres that are standing here is that this robot, which is a rolling sphere, it cannot submerge. So we can submerge, so we can have a subsea as well as a surface presence. And we think we're a good candidate for that. So bearing in mind the video of the robot crawling up onto land is an example of how, for example, in a contested logistics situation, we can pull supplies to shore. We can stay beneath the surface, obscured and out of danger of being flipped by a wave that might, a fate that might afflict a unmanned surface vehicle. And one of the characteristics of this fin thruster is it has very good static thrust, very good bollard pull. So its efficiency relative to the propeller goes up the more resistance it faces in making its way through water. And it has very good traction on land, so we envisage it towing payloads up onto the surf zone, if not up onto the sand, at least into water that's ankle deep. And we were contacted by some active duty medical personnel within the Navy about helping them solve a problem for a Navy SEAL rescue, another type of diver rescue. So on a right now, if a Navy SEAL, let's say an amphibious landing, if one is injured, there is really no way to evacuate personnel other than sending in a helicopter, which of course gives away position and can be shot down, or sending in a surface vehicle, surface craft, which of course is more visible, louder, and the surface vehicle also has a danger of being flipped over in the surf zone. So what we discussed with them, and this is a program that is funding is being sought in the background by other people involved with us, is to have a rescue pod, so a diver rescue pod. And we worked a little bit with them with the schematic on the right of what would be needed in that rescue pod. And our focus is the tow vehicle that would tow the rescue pod, quickly get below the surface and tow the rescue pod a kilometer or two to awaiting to a rendezvous with a medical ship or another vehicle out at sea. And our conception is to have a medical personnel go along with the injured diver rather than having them being towed out alone in the vehicle. And this is a conceptual stage, but it's an example of the sort of unique things that our vehicle can do. And this one here is, again, it's to show some of the possibilities. So this would be a frogman, a thruster, a diver assist that the diver would hold on to or be connected to in some way. And one of the advantages of our system for such a diver assisted vehicle is that, as I mentioned before, the higher the drag load, and a diver with all his equipment is going to be a pretty high drag load, the more efficient the fins are relative to a propeller. And the other advantages for a diver assist such as this, in addition to very high efficiency, so longer battery life, is very high maneuverability. The fins have a very tight fin position, and what the vehicle is doing are very tightly correlated. So you move the fins to move forward like 3 inches, and the vehicle will move forward close to 3 inches. You can also reverse back up very quickly. Very good yaw control. No danger of a diver's hands or straps or other equipment getting caught in propeller blades, and stealth, because we don't have spinning blades. We don't get blade tip cavitation and vibration. So it's a stealthy, very safe, and very quiet system that I think lack of noise in terms of distractibility and focus is probably also important for a diver to have a very quiet system, as well as a safe and highly maneuverable one with high energy efficiency. This slide here, this is an upcoming contract.
Pietro?
Yeah.
This is Eugene. So everything that you're showing right now, it's the same vehicle. Is this scalable? So could I make it wider to hold other platforms, larger platforms? Could I change the length and the width of the fins? Could you cover that? How scalable it is?
So in the water it's entirely scalable. On land, there will be limits as to how much weight, because the fins are the fins are both soft and hard at the same time, but there is still a limit to how much weight they can hold on land. For an underwater application, essentially we have the 2 thrust modules. So we have these 2 fins with their own thrusters, and then we have the electronics and control. So this vehicle here would be very easy to move the fins apart with their thrust modules and have a much wider deck, for example. When it comes to making the fins larger and the thrust modules that control them larger, that's we could do as well, but it would be a re-engineering project to make everything larger. Absolutely doable, but right now, the vehicle of this current size, without doing any more engineering work, we go to this slide here. Without doing any more work, we could take these 2 fins and this thrust module with a controls package that's already included, and we could put this on anything potentially. So imagine sticking this onto even on a surface craft if there was use for that. Be fairly quick to adapt. If you wanted to have a much larger vehicle, larger fins, larger thrust modules, higher power, then it would be there will be some redesign. But it's certainly, we for DARPA we prepared a white paper for a large open ocean swimming vehicle, and it hasn't been funded yet, but those kind of projects are on the drawing boards. It's sort of waiting for the right opportunity to express themselves.
All right, thank you.
So this is a contract we're starting It's under contract negotiations. It could be any day now. And this is for an open ocean vehicle from mine countermeasures vehicle. And this is, I don't know if it's a little small to see these details on the screen, but this vehicle has 4 fins instead of 2, which is the Seabed vehicle I've been showing up until now. And the 4 fins give it extraordinary maneuverability. So we basically have holonomic control and a very tight interface between what the fins say the vehicle could do and how the vehicle responds. So it's highly responsive. And for this project, we are collaborating with the Army, with ARL at Penn State and the Naval Surface Warfare Center at Panama City. They're developing a novel synthetic aperture sonar to go with this vehicle. And why they want our vehicle to as a test bed for this new sonar, we don't yet know. They may never tell us why, because I believe that will be a classified program that we never really get a peek under the hood, but we are going to be providing the vehicle. One of the things they mentioned was our vehicle's ability to perform tight spirals in the water as being something potentially valuable for what they have in mind with this program. These are, and I showed the video first because most of what I'm showing is renderings, kind of cartoons, but I wanted to show the video to say this is well beyond the rendering stage. There's a real grainy, real video of it out there in the world getting dirty. So this is an application that we've considered for some time for cable or pipeline inspection. And on the top row, we're showing a conventional AUV following a pipeline doing a scan. And in such a mission as they currently performed, the autonomous vehicle performs a scan. At a certain point, it will surface or be retrieved, and the data will be reviewed. And any anomalies that were detected during the scan, a surface ship will be sent with an inspection ROV, and then maybe another ROV will be sent down once they see what the problem really is with the right equipment and the right to deal with it. So with our vehicle, because we have cruising ability, but also very high maneuverability, we're proposing that we can do a scan of a pipeline. And with onboard AI that is under development, if an anomaly is spotted, that the vehicle can go in and take a closer look, maybe take high resolution images, maybe even take a water sample, and then continue on its mission, meaning that at the end of the mission, when the data is reviewed, perhaps what looked like bubbles was just jellyfish, and there's no need to send a surface ship to go and perform an intervention. And given that the data is going to be able to gather is going to be so much richer, if intervention is required, then the right kind of ship with the right kind of equipment and supplies can be sent to actually perform the intervention. So I showed the ice skating. It ice skates extremely well. Something we've not explored because we're a small company of 5 people, and we can't pursue everything at once. Even though we see tremendous number of possible applications for this fin technology we've developed that nobody else that we're aware of has been able to do. I've got a slide of the Arctic Circle I put together showing just how much is going on here. Oil, gas, minerals, and with the melting sea ice, sea passages, and contested territorial claims. And this is a potential hotspot in the future. So this is a view of an Arctic camp, and they've got more and more there's water and ice mixed together. So with a vehicle that can skate where it needs to, crawl through the snow where it needs to, using its crawling as opposed to skating, and then be able to move through the water, we think there's potentially great value for our platform in Arctic and Antarctic scenarios. We can also, swimming under the ice, we can also station keep by raising the fins and becoming slightly positively buoyant. So we can stay under the ice, maintain our position by station keeping, and then swim or emerge or as desired. And this is this is a into the future, ambitious, futuristic alternative method for seabed nodule mining. And I put it up here with this audience because the U.S. government is getting increasingly concerned about our reliance on China and other other powers for critical minerals, not only critical for our industrial base, but of course for the defense industrial base in particular. And polymetallic nodule mining is a big topic. I could do a whole presentation on it, but we're proposing that with the speed at which we're developing the capability of our robots, then rather than using the gigantic tracked crawlers that are currently planned to plow through the sediment and suck the nodules up, that we could apply our robots and to selectively collect the nodules, place them in baskets that get floated to the surface. So we've got an autonomous swarm on the seabed that is collecting nodules without plowing up the surface, without killing the organisms that people worry are going to be disrupted in that deep sea ecosystem in the abyssal plains. And this is sort of a related to that. Scallop trawling, scallop fisheries are a very multi-billion-dollar industry in the US alone, but they're very destructive. The current method using these weighted trawl nets. This is a picture of a scallop bed off the coast of Scotland, actually, before and after trawling. And so we're proposing using the same technology for picking up nodules, polymetallic nodules, that we can do that for something such as scallop harvesting. And obviously, if you just remove the scallops and leave the ecosystem on which the scallops depend intact, that the scallops population is going to recover much more quickly, which ultimately will help out the scallop industry overall. A less glamorous potential application, given the unique things that our vehicle can do, is sewer and culvert inspection. And on the right, there's this poor guy in a sewer line, and this is actually fat. And so there are propeller vehicles such as this one by Video Ray on the left that can swim through watery parts. But it's a propeller-driven vehicle, and once this gets very shallow, this culvert, it can only go so far. There are tracked crawlers that are made for culverts and sewer lines, but they are necessarily heavy. And if, for example, there's a lip here or a drop, then the tracked crawler won't be able to get up and into the culvert, and a propeller-driven ROV won't be able to go through the dry parts. And a propeller-driven ROV obviously couldn't go through here, whereas we can crawl and swim and do whatever is needed. And that's a commercial application with potential civilian, with defense applications as well. I mentioned very quickly aquaculture. Again, I'm getting into the more civilian side of things. Stress in fish farms, floating fish farms, for example, caused by ROVs. It leads to a reduction in fish growth. So here's a diver in a netted fish pond. And here is an ROV in a netted fish pond. And here is not our ROV, but a non-propeller driven ROV. This one has little flippers. And the fish, that causes way less stress for the fish. And it allows you to get up close to the fish if you want to inspect them for parasites and so forth. So this just is a slide of our patent portfolio. These are patents that we have on this technology. This is just this is Jeff Bezos, believe it or not, just to sort of show that we're gradually becoming known to the sort of tech enthusiast world in general. Jeff Bezos holds a 3-day event, and we were invited last year. And this is our Sea Ray platform. This is Jeff Bezos in ROV mode. Had fun rolling it around the stage. This slide is probably too small to see, but I wanted to see if I can get some point across of the history of our funding. So we started our first funding. Our first funding was in 2011-12. These were SBIRs from National Science Foundation, USDA, the Navy, and so forth. These are actually early energy harnessing implementations here around 2013. We were like 2 to 3 people for quite several years while doing this, laying the groundwork for this robot up here. We started as an energy harnessing company, and we're called Pliant Energy Systems because the original goal of developing this finned mechanism was in energy harnessing. So in a fluid flow, fluid moving over the fins actuates the fins, and you convert that mechanical power of the fins into electrical energy or other useful mechanical work. And we developed our first prototypes were generators and pumps, and they were I would say they were quite successful. But when it comes to electricity energy generation, there's an infinite number of ways of doing it, but it has to be super cheap to compete with existing solutions and very reliable. And the R&D trajectory to develop a hydrokinetic generator using our fin system was belong. Much low-hanging fruit is to develop a robot using those fins as propulsors rather than energy harnesses. And we were able to attract much more funding that way. It's surprising there's more, not surprising there is more money, has been in recent years for robotics than for energy harnessing. But the fins still can be back driven and used as generators. So this is actually this image here is of a second.
Pietro?
Yeah.
But there's a question in the comments.
Yeah.
From Tom Russell. He wants to know if you're going to be at Navy Sea Air and Space next month. I believe. Tom, is that in DC? That's the one at the Gaylord.
Yeah,
That's correct, Gaylord.
We were there last year. We don't plan to go this year. We might attend. We can, if you think it's worthwhile coming down to meet you or some people, we can attend. But last year we were at NRL's booth and we had the Sea Ray vehicle there. I'm happy to follow up on if you think that's a worthwhile thing for us to do. I'm happy to follow up.
Right, so where are you located at? Where are you?
We're in Brooklyn. We're in the Brooklyn Navy Yard. Now it's a civilian facility in New York City.
That's funny. I was actually stationed there for a year.
Oh, you were?
When I was in the Navy, but we'll talk about that later.
Yeah, sure. And so this is energy harnessing. This image is of an energy harnessing device that we tested at the University of New Hampshire last spring, and it looks just like the robot, except that this is a passive mechanism. So one of the potential values of our vehicle is if it can self-charge. I mean, in ambient flow in like a deep sea ocean current, you've got what 0.25 meters per second flow. The fins there's just not that enough kinetic energy in most marine currents to generate enough power to recharge your thrust battery. The batteries powering your thruster. But if we can go out to a location as a robotic vehicle and then tether ourselves in that, then the flow moving over the fins, moving them backwards, would be enough to power, say, some sensors. So we could have a persistent, indefinite presence powering sensors using the thruster fins as energy harnessing devices. So I think that's a good summary of the vehicle and where we are. And I'm thinking what I might do is just leave this looping in the background while we have questions, if that's of interest.
So does anybody have any questions before I start asking mine? If you're talking, you're muted. All right. So in your application that you just referenced, or your stationary.
Yeah.
What how would you remain stationary? Or would there be some drift? So
we'd have to attach ourselves to the seafloor. There are various tethered, harpooning. It would be a project in collaboration with somebody there's a lot of people that have worked on ways to attach yourself to the seafloor. So it might just be something like an anchor. We might develop something more sophisticated. If it was an environment with posts and rocks, it would be easier. But yeah, we do need to not be moving so that we are fixed relative to whatever current there is.
Right now, also you're showing different types of fins.
Yeah.
Like here, you've got studs on a fin.
Right.
Are those for different applications? Does the one for working on the ground, does it function as well as in the water? The ice one.
Yeah, so they're all, so partly is it's been, so there are thousands of hours of multi-physics modeling over the years that's gone into making the fins be able to do what they do. And that's where really our IP, our key IP is. So you can see in this one, there's the fins they're just plain rubber. In the ice skating version of this robot, so this Velox robot is ice skating. It has the same fins, but it has a very thin metal blade at the edge of the fins. And so that's why it's able to ice skate. However, that can swim just as well. You don't have to take the metal blade out to have it ice skate. This is moving through. Yeah, I don't know how autoplay is working here. And this one, the fins are, we don't really talk about what's in the fins, but it is not as simple as just two sheets of rubber, put it that way. And the reason why there's so many different fins in this video is really more a case of us trying out different things. I will say that if this was only going to be swimming, then the morphology of the fins would be optimized for that. The fins have a very strong three-dimensional shape on the versions of Sea Ray that crawl, and all Sea Ray versions are for crawling. So that gives more strength to the fins on land. They have a more three-dimensional shape. If it was never going to have to crawl on land, the wave form would be a little different, because there are various terminologies, just such as the optimal specific wavelength, that marine biologists have learned in terms of the fin amplitude, wavelength, and so forth. There are ways to optimize it for swimming only.
Okay. So Tom Russell has a few questions for you. You want to go ahead, Tom?
Yeah, thank you. So, and again, I apologize if you covered it and I missed it, but the operational depth, these obviously go down. How deep do they go down?
Well, this is rated for 100 meters. There's
Okay.
nothing so there's nothing about our platform that prohibits going deeper. It's just that we've rated this for 100 meters, given that our obvious advantage is shallow water. We can,
And then what about, and talking about on the water, perhaps under the water, the speed and range?
So this is a 4-knot vehicle. So we only have 2 of these. One of them is out at MIT. So MIT's been collaborating with us, the MIT Marine Autonomy Lab, on the Autonomy. So we're using the Moose IVP helm, for people that might be familiar with it, as a middleware. So we have 2 vehicles only. One's at MIT, one is here in New York, and it has a top speed of 4 knots currently.
Mhm.
Interestingly, it can go from 4 knots to 0 in half a second, because the fins are great for swimming. As soon as the fins stop, they become massively draggy. So the vehicle halts almost instantly, and then it can accelerate and reverse. It's like it doesn't have a front or back. It does when we have the tether, but as far as the rover's concerned, it has no front or back. So it can stop, halt instantly, almost instantly, and then reverse at the same speed that it was going forward. In terms of the range, we had Velox, this little one. This is the precursor. We had this swimming at 2 knots for 4 hours, and that comes down to the battery pack. So we have, and both these vehicles are internally powered, and it depends on the size of the battery. I couldn't tell you yet how far Sea Ray, this one, the larger one, how far it can swim at 4 knots. We haven't done that yet. But these are things that in the next few weeks we hope to do a series of tests to be able to give these performance matrices such as the ones you were asking, Russell.
Thank you.
So Pietro, but do you have the ability to add solar panels to the surface of the vehicle, and where it could actually come up, recharge, and then go back down?
Yeah, by all means, this could be wider and flatter, because each fin is individually powered, and it's really these two these 2 aluminum shafts here. Those could be spread out, and the body could be much wider, and we could bask the surface to recharge. By all means, it might take a while, but it would depend what latitude we were in. But the form factor here is not set by anything other than what's going to be in the core here, and how flat it could be. It varies.
So now, do you have ideas for payload? Like do you have, there are vehicles that I've dealt with before that have specific design for they give you basically a box, and you put your payload inside of that box.
Yeah, so we have right now, this has an empty, so it's a 4-inch tube. We're going to move to a 6-inch tube in the middle. Let me go back a little bit to this one. So hang on a second. So we have in this version of Syria, we have a 4-inch tube. We're going to move to a 6-inch tube. These are the 2 thrust modules that work independently of each other. We have cameras front and back. We have lights front and back. We have this section here is currently empty. So that's a potential payload bay. And we have this full of batteries, but almost entirely batteries, because we want to be able to have long duration missions. We haven't actually tested it yet to see just how long it will go. But given that we have essentially a standard tube, there are a lot of payloads could be added to this tube. In the modular payloads, the payload modules exist for common AUVs could be inserted here. I mean, right now we have a DVL compass, we have a IMU, we have a Wi-Fi, we have a Wi-Fi radio antenna, and so forth. So we've given it sort of the basics, and we didn't put things in it beyond that because we want to find out what people want us to put in it to get some better idea of the kind of missions people see this being used for.
Okay, and that's where the community can help.
I hope so, yes.
Okay. Any other questions? All right. Pietro, is there anything you wanted to add?
I think that's, yeah, I mean, I had a lot more material, but I sort of stripped it down because there's already a lot in this, and
Well, I would cover slide 19.
Slide 19.
Because you still have 10 minutes, so.
Yeah, so this is just eye candy at this point, right? But
right.
This is with our upcoming O&R contract for we call it MCM rig, it's a mine countermeasure vehicle. Because we have super maneuverability, we present this as the sort of, so my understanding is that the subsea community is very wary of having an AUV, an autonomous underwater vehicle, come close to like a submarine, because that nobody really trusts the autonomy yet. And the conventional AUVs have they're not maneuverable. They're very good at cruising. The technology's been refined to a very impressive state, but they have enormous turning radiuses and they cannot stop quickly. Take a long time to slow down, and they have very poor ability to correct course in a short time period. So we're proposing that the kind of agility that we expect to have with our next vehicle would enable this kind of maneuver. Now, if this was a moving submarine, we don't have the speed. If this was a stationary object, such as a submarine, we can perform scans such as this. We think we will be able to perform scans such as this. That with an autonomous vehicle that right now I don't believe anybody, at least in the public domain, nobody is doing these kind of maneuvers. Nobody has the ability, or nobody trusts the ability of an autonomous vehicle to perform such a scan. Obviously, this is an enemy object. We're less concerned about damaging it, although not necessarily, because you don't want to cause an international incident because your AUV has damaged, or triggered something. So that is what that slide is about. I didn't show it because I wanted to focus on the real things that we've done, to show that what seems like sort of sci-fi is actually close to being a reality. And we're not far from being able to do this with it. Maybe we won't do it with a submarine anytime soon, but with a test object. And a lot of that comes down to our collaboration with MIT on the autonomy that we've been developing with them. I could show another video.
Yeah, I mean, those are the kind of things that make you unique, and that's why I wanted you to show that, because this is also what we try to do, is we want to get people thinking. We want to get people to look at what is new, novel, and different, and see the different applications, because just something like that picture there, yeah, it may not be related to submarines, but it could be related to underwater piping or inspection of underwater fiber optic cables or whatever. I mean, so I just want people to understand what you're thinking about the future looks like, so that they can actually think along those lines as well.
Right, that makes sense. Yeah.
All right. Any other questions? Did you want to show that
yeah.
last video?
Yeah, we could. You want to watch that? Yeah, the last video. Well, I was going to show also, since we have a few minutes, I was going to elaborate a little bit on the nodule mining. And some people, yeah. So this is currently how it's being performed. And there are some pilot projects out there now. So like I said, it's a big subject. Polymetallic nodules are these potato-sized nodules that sit on the ocean floor in vast numbers in the abyssal plains. And the most, it literally looks like this. I mean, this is a render, but this is how dense they are. And they contain copper, cobalt, manganese, and some have lithium and tin and so on and so forth. They're just pure metal. And right now there is experimental mining going on to raise them using, it's really taken from the mining industry or the construction industry. So these large tracked crawlers that go along the surface and they scoop up the top layer of sediment and they kill anything that might be in the way. and they pump up the mixture of nodules and water and slurry up to the surface, a surface vehicle, and at some point you have to, and the nodules are separated out, and the slurry has to be returned at some point in the water column. And they use the pumped riser from the oil industry. And one of the main, so it's a technological challenge because these nodules occur at 4 to 6 kilometers in the abyssal plains. There's also a big political problem they have in the environmentalists, and a lot of corporations and countries have come out and said, we must never do this. And one of the reasons they say we should never do this is because of they're worried about the effect on the deep sea abyssal plain ecosystems. So to have us, and even though the biomass down there is very low, there's no light. There's quite a lot of biodiversity, microfauna and macrofauna. And so we're proposing that using a swarm of robots that don't touch the seafloor, don't touch sea life, and just raise the nodules individually, place them in lifting cages that go to the surface. It's more like we think it's in addition to being less environmentally harmful, and therefore being more likely to overcome the opposition from environmentalists that are putting great pressures on their governments to not allow this to happen, even though everybody knows we're going to need huge quantities of metals in order to decarbonize and electrify the economy. In order to overcome the opposition to propose a less environmentally damaging way of doing this. And I think it's probably potentially a more economically viable way of doing it because the cost of this riser it's a very high capital expenditure to make these gigantic machines, to make this gigantic risers that are both single points of failure in any mining operation. So if something goes wrong with the riser, everything stops. If a single bolt blows in the caterpillar track of the crawler, the whole operation halts, and there are many people, many man hours going to waste as the operation stops. Whereas this is more like a distributed operation, that more like packets. So you're sending up the nodules in packets, and the robots, any one of them can fail. The operations continue. And if you lose a nodule cage, it's okay. The operation continues. It's all about sort of distributed collection and distributed retrieval of nodules to allow 24-hour operations.
That is fascinating.
Yeah, thank you. And if you wanted to see this video that I brought up briefly, this is a pump. So there's no electronics there. And so it's being towed through the water to simulate a river moving past it. So it's the same as if it was fixed and the river's flowing. This is at the UNH tow tank. It's being towed to represent that. And then this is everything's made of plastic. Everything, this pump can be put together by hand, no tools required. It can be disassembled by hand, no tools required. It's all plastic components. It's a prototype, and we're getting about 800 liters per minute at modest water flow. So water is pulled in through the front of the vehicle and squirted out through this tube here. And there are a series of modules that do the pumping. So the fins are doing this heaving action. And then in between the fins, you have these modules that create a pumping action. So it's a very simple, very cheap hydrokinetic pump. It's a one-off. We tested it once, and now it's a museum piece for now, hanging in our lab because, this is a third world application, right? If you could have these in dirty streams and rivers, filtering drinking water in parts of the world where people are still dying regularly of diarrhea and sleeping sickness and so forth. But it's a whole different world to get into, to get the funding to develop this technology. But I show it is because what is essential is the fin. The fin is our key piece of IP that nobody else, for reasons that I don't know, no one else figured out how to do it. If anybody's ever seen an effective swimming vehicle, I'd love to know about it. But so far, you see something and it kind of flaps away and it's barely moving. So that's kind of our
I have people that I'm talking to now that would have application for that. So we will definitely present that to them.
Well, thanks everybody. Thanks Eugene for arranging this. Thank you everybody for listening.
And please again put your contact information in the chat.
I'll do that.